Anyway, what's going on, folks? Let's start up with some example problems. And the first example problem we're going to do is pulling a sled in snow, which none of you have very much experience with, I'm sure. That's what I love about these physics problems is all of these textbooks are written for mainland people, so they're all full on like, a trolley is going this way. And the students in Hawaii are like, what the heck is a trolley? Anyway, yeah, funny anecdotes. So why don't we do this? Why don't we just say, I gotta go. Ready? You guys go down to the beach, right? Sometimes.
Sometimes.
And you're pulling the boogie board, and you have your picnic basket on top. And you guys know this, right? It's like it's so hard to carry all this stuff. So I just put everything on the boogie board and I pull the boogie board, right? You guys, you do it. I know you do. All right. So let's read the problem. A 4 kilograms boogie board is pulled across the smooth ice surface. So let's say a 4 kilogram boogie board is pulled across the water. That is, you know how when the water goes up on the beach and then it kind of like you can skim the board across? Let's pretend we're in that situation. I'm just trying to make it relevant here. So the mass is 4 kilograms. Are we cool? And the force acting on the sled is 620 newtons and 35 degrees above the sled, above the horizontal. Okay. So the boy, or the girl, doesn't matter, is pulling with a force of 600, is it 620 or is it 6.2? I can't see that. Can you read that?
6.2.
All right, 6.20 newtons at an angle of theta equals 35 degrees above the horizontal.
Yeah.
What is the acceleration? Is that what it's asking?
It's asking if the sled starts at rest, how fast is it going after being pulled for 1.15 seconds?
Okay, all right. So it's got, if it starts at rest, basically this is physics' crazy way of saying, hey, remember that stuff that we learned back in chapter 2, which is like the kinematics equations? We can still apply those here. But essentially what they're asking for is, what's the acceleration? So let's figure out what the acceleration is, okay? First thing, vector. Do you see a vector that is not in the x or y direction, but it's in both? Yes or no? Alice, use your big words.
Is it the newtons?
I see a vector. I see an arrow that is going in at an angle. Immediately, before I even start the problem, I take that vector that's being pulled in at an angle and break it up into its x and y components. So this is the same trick we did back in two-dimensional motion, right? We didn't even, we had a velocity initial, and it was going at an angle, and immediately, before we even thought, before our brains kicked into gear, we used SOHCAHTOA on this sucker, right? Do you remember that, vaguely?
Yeah.
Okay. Well, we're going to do the same thing. We have an F, we have a theta, so immediately my brain kicks into f of x, f of y, kind of deal. Are we cool? F of x is equal to what? This isn't a trick question, this shouldn't even be hard for you. Kaylin, I'm counting on you too. No, f is equal to 6.2. What I'm asking is, what is f of x?
6.2x.
No? It's f cosine theta. Right? You remember how to break up a triangle its components, right?
Yeah, I just forgot how to spell like SOHCAHTOA. Sorry.
Oh, you forgot how to spell SOHCAHTOA?
Well, like it's at the H. I don't.
Right. Okay, here. Write that down in your notes. Okay, now do you know what f of x is equal to? Or I should say f sub x is equal to. It's 6.2 times the cosine of 35.
Mm-hmm.
Whatever that is. I don't even care. I don't even know. Okay? All right. What is f of y? There's only 2 people in this class, so there's a 50-50 shot I'm calling on you.
So like, is it
Since you're sitting right in front of me and Kaylin, I can't pick on her virtually. I'm picking on you. I'm sorry.
F psi?
There we go.
Okay.
You know this. You know this.
Yeah, I was just looking.
Yeah, I know. You know this. It might take a little bit of time, but you know this. We cool? Kaylin, are you still alive? I know you've got a lot to deal with sometimes, so I'm not going to bug you too much, but yeah. Is it from the bottom right corner? Well, I think what Kaylin's asking is, wait, which side is the opposite side and which side is the adjacent side? Because that will tell me whether I'm dealing with cosine of theta or sine of theta, correct?
Yeah.
And my answer is, it depends on the angle, on how I define the angle. I define the angle to be 35 degrees above horizontal. So that means this bottom left-hand corner of the triangle is theta. If that bottom left-hand corner of the triangle is theta, then the side that is closest, or that is touching theta, but not the hypotenuse, which is this side right here, is the adjacent side. And the side that's opposite of theta is the opposite side. Make sense? If somehow, how did I know which corner x is x and y? X and y isn't a corner. It's actually the horizontal part of f, and y is the vertical part of f. Is that what you're asking? So there's no corner associated with these f of x and f of y. It's the horizontal and vertical parts of it. Do you get it?
I think so.
Okay. Kaylin, good? This is the exact same thing I did with you folks in the lab on Wednesday last week, and this is the exact same thing I did when all we did was change this f to a v in 2-dimensional motion. How would you find f of y? Why would you know which angle you're using? Oh, okay. All right, fine. Let me show you exactly where these f cosine theta and f sine theta come from. Okay? I know that the sine of theta is the opposite over hypotenuse. Okay? If this is theta right here, then the opposite side would be right there. Cool? And I label that opposite side as f of f sub y. Are we cool? Divided by the hypotenuse, and the hypotenuse of this is f. I want to figure out what f sub y is, so I multiply both sides by f, and I get f sine theta is equal to f sub y. Are we good? Which is right, why I wrote an f sine theta up here. Okay. You go through the same exact trick, but just change this to a cosine of theta, to figure out this part over here. Are we good with that? Okay. So you need to be able to do that like the back of your hand. And people say that expression, which basically means you look at the back of your hand all the time. You need to know how to do this and be as familiar with this process as you are with the back of your hand. It has to be like, boom, second nature to you. Okay? In physics, breaking up a vector into its components is extremely crucial. In fact, that's all of our lab. All our lab was last week Wednesday was that. And Kaylin, you were at the lab, so I'm surprised that this isn't like immediately easy for you. All right. What we're going to do now is we want to figure out what is its acceleration. So I'm going to add up all the forces in the x direction. Okay? And that's equal to the mass times acceleration in the x direction. I can't remember, Alice. Have I taught you F equals ma yet?
I don't think so.
Okay. I haven't because you haven't been at the last few lectures for last week. Essentially, with this chapter, all we're going to do is learn, you know how like in the previous chapter we learned 4 equations?
Yeah.
In kinematics, we learned 4 equations. And we needed all 4 of those equations for one-dimensional motion. And then when we got to 2-dimensional motion, I didn't teach you any new equations. I just taught you those 4 equations with SOHCAHTOA on top of that, right? In this chapter, I'm going to teach you 1 equation. So you don't even need to choose which one of the equations I use. I know you know exactly which equation you're going to use. It goes F equals ma. Cool? Easy enough?
Yeah.
I'm going to have a funny looking symbol in front of it. It looks like this. Have you ever seen that symbol before? We use it in math sometimes. I don't know if they've used it in math that you've been in.
No.
Okay.
No.
This is the summation symbol. It just means add up everything.
Okay.
Cool?
Yeah.
So you're going to add up everything. That's it. Now, in 2-dimensional motions, we did that trick where we looked at things only in the y direction. And we looked at things only in the x direction, right? I kind of think of it as like putting on our y direction glasses on and putting on our x direction glasses, right? So we had our standard delta x equals v naught t plus 1/2 at squared. But when we applied it to the y direction, we would change this to a y, and then we would put little subscript y's over here, right? To signify we're talking about the velocity in the y direction, the acceleration in the y direction. Are we cool?
Yeah.
We're going to do the same exact thing here. So I could make this an x, or I could make this thing a y, depending on which direction I'm looking at. We good?
Yeah.
Now I don't put a subscript on m because m stands for mass. There's no such thing as mass in the x direction versus mass in the y direction. Your mass is your mass. If your mass is 4 kilograms, it doesn't matter whether you're talking about the x or the y direction. It's 4 kilograms in both. Does that make sense?
Yeah.
All right. So the equation I'm going to, so really, I don't know if you want to say, well, really, Mr. Daldy, you're teaching us 4 equations, or 2 equations. Look, those are 2 equations. And I'll be like, come on. This is not 2 equations. This is the same equation, just looking at it in different
Wait.
directions. Right?
Mm-hmm.
Okay. So we're looking at the x directions here. What I like to do here is I like to draw a free body diagram. A free body diagram just says, let's pretend that there's this thing, this boogie board is a point. And let's put the forces that we see acting on it. What forces do you see that are acting on this thing?
The person's
the person pulling it. Okay? F. What else do you see acting on it? There's one more force that's pulling on this.
Like like below the board.
No.
Oh, gravity.
There we go. I'm going to let you make that mistake one time. This is the last time. A lot of students say gravity. Oh, it's gravity. That's the force. No. Gravity is 9.8 meters per second squared. Gravity is an acceleration. But what you mean is the weight. Right?
Yeah.
That's what you mean. Which is equal to mass times gravity. Okay?
Okay.
So, next time I ask you what force is acting on it, and you want to say the weight, you either say the weight or the force of gravity.
Okay.
Okay? Sometimes I might write that as a W, sometimes I might write that as an F little g. It's the same thing. Cool? All right. Now, I'll just put that in stuff. In order to simplify this, I said, well, we can really take this F and break it up into two components. I can replace that with a Fx and Fy. Right? Okay. So, sum of the forces equals mass times acceleration in the x direction. What forces do you see acting in the x direction? Let's add them all up. That's what this means.
Okay.
So what forces do you see in the x direction?
F cosine?
F cosine theta. Is it a positive or negative? Oh, you don't know because I forgot to tell you which direction is positive and negative. Let's make it things going that way is positive x and things going up is positive y. So this force right here, F cosine theta,
Is it positive?
is a positive. Right. Do you see any other forces in the x direction?
No.
Then we're done with adding up all the forces in the x direction. There happens to only be one. Got it?
Mhm.
And this is equal to the mass times your acceleration in the x direction. Are we cool?
Mhm.
So, can we solve for my acceleration in the x direction? Sure. Are we cool?
Yeah.
Now, normally you would be done, but this problem asked you something different. It says, if we were to start this thing from rest and let it go for how long?
1.15 seconds.
So time is equal to, so this is the separate part of the problem. T is equal to 1.15 seconds. The velocity initial is equal to 0, right? This is starting at rest. And then what did they ask for? Did they ask for the distance it traveled or the speed it's going?
The speed.
Okay, so V final is what we're looking for. And the acceleration that we have is
6 point.
F cosine theta over m. So what does that leave? That leaves the delta x as our dk dc. Which equation doesn't use delta x? I think it's the first one. V final equals V initial plus AT. Right?
Yeah.
So, V initial is 0. A is this number. T is 1.15. So V final that we're looking for is F cosine theta over m times T. And that, my friend, is your solution. You should plug numbers into there. So let's do
6.2 times the cosine of 35 divided by, 6.2 times the cosine of 35 divided by 4 times 1.15. Someone use a calculator for that?
Actually, I'll do it. 6.2 times the cosine of 35, close parentheses, divide that by 4, multiply that by 1.15. I end up getting 1.460.
Meters per second.
We cool? What did they say for the answer?
Oh, I did it wrong. Oh, oops. I know what I did wrong. The mass is not 4, it's 4.6.
Sorry.
I wrote down the problem.
Alright, so that would be 6.2 times the cosine of 35 divided by 4.6 times 1.15. 1.27? Or wait. 6.2 times the cosine of 35 divided by 4.6 times 1.15. 1.2696 or 1.27.
Yeah.
Cool. That's the answer.
How's that?
Hard? Easy?
Easy,
Easy-ish? Easy-ish?
easy-ish when you get like through half of it at least.
Yeah, the first half wasn't hard. The second half wasn't hard either. Wait. Okay, let's see. Let's try this one. Actually, let's go backwards and we'll do this one. Okay, here we go. Read that problem.
Okay. I'm going to do another problem for you. You
Wait,
ready?
the Jack and Jill one?
Jack and Jill.
Okay.
And read it out so I can hear you.
All right, you ready? Go.
Jack and Jill lift upward on a 1.30 kilogram pail of water.
Okay, wait. Mass of pail is equal to 1 point what?
3 kilograms.
3 kg. Okay, got it.
With Jack exerting a force of magnitude 7 newtons
Okay.
and Jill exerting a force of magnitude 11 newtons.
So, okay, and then did they tell me the angle that Jack is pulling at?
Jill's angle is 28 with the vertical.
Okay, so here's the vertical,
Okay, so 28.
and let's make this Jill right here. This theta equals 28. Oh, here, no, I think this is, we'll make this theta equals 28. And what was she pulling at? A force of what? 11 newtons?
11 newtons.
So we'll call her force 1 is equal to 11 newtons.
And Jack's one is 7 newtons.
Jack is pulling less than Jill?
That's cool.
And then the question is, at what angle with respect to the vertical should Jack exert his force if the pail is to accelerate straight upward?
Okay. So, this is force 1, which is Jill. I don't want to call it force J and force J because
They're both J.
they're both J. Okay, so force 1 and angle 1. This is force 2, angle 2. Cool? And what other force? Let's draw the free body diagram. So the free body diagram would basically take this picture and make it a dot. So I have force 1 acting at theta 1. If it's all right with you, I'm not going to put in any numbers, but you can just associate the numbers back and forth. We cool? And I have force 2 acting at theta 2. Cool. What other force do I have acting on?
Wait.
Ah, there we go. Good. You didn't make that mistake. The weight. Which is equal to the mass of the bucket times the gravity. In this case, gravity is 9.81 and all of that kind of stuff. Are we cool? All right. So, is there a part A and B to this question?
Yeah.
Is the part B like what is the acceleration?
Yeah, it says determine the acceleration.
All right, cool. So, let's do this. In order to solve this, I always need a coordinate system. So, we'll do our x and y. Nothing funky there. Cool? I just say anything going to the right is positive, anything going up and down is positive, or up is positive. We cool? All right. Immediately, when I see a vector, let's draw out the picture very carefully. F1 is over here. Now, Kaylin, pay attention to this because this might freak you out. I'm going to call this F1y, and I'll call this one F1x. Are we cool with that? Because I take my F1 and I break it up into a triangle. The approach I'm going for here is, before I even start the problem, let's break these forces that are going off at angles into their x and y components, right?
Mm-hmm.
All right, and this is something I'm always doing, so it shouldn't be a surprise to you. Angle theta is over here. So what is F1x equal to? Oh, I'm sorry. I'm going to put a theta 1 over here because. So F1x is equal to what? Kaylin, I want you to answer this if you can. You can do it too, Alice.
Sine?
Good. It's F times sine of theta. And F1y is F1 times the cosine of theta. Alice, how did you get that this is sine of theta?
I just went with where the angle was, and then went from what we have like x and y, so I just went like opposite, and then
The reason why I said Kaylin, pay attention to this, is because this is exactly Kaylin's question. You notice in the previous problem, when we had our triangle that looks like this, f of x was actually f cosine theta.
mm-hmm.
Whereas in this problem, f of x is actually f sine theta. Do you notice that? In this problem, it's f cosine theta. In this problem, it's f sine theta.
Mm-hmm.
And people are wondering, what the heck? Why isn't it f cosine theta? Because it usually is cosine theta when we're talking about the x direction. And my answer to that, and it's exactly what I was trying to fool you with, but you were too smart for me, is that it depends on where you call the angle. And in this case, we called the x direction as the opposite direction, or opposite side of our angle theta, which was defined with the vertical, right? So therefore, that's f sine theta. Does that make sense to you, or are we?
It makes sense. I just got stuck because I didn't. I was thinking like maybe it's tangent, but then we don't have.
No.
Yeah.
You almost never use tangent when you're breaking things into its components.
When would you? When would you use
You
it?
would use tangent when you have the x component here and you have the y component here, and you want to figure out the angle.
Okay.
We did that back when we were doing velocities, where you were able to calculate out vx and vy, and I wanted to figure out, well, what is v and what is the angle of v? Then you would use tangent
Okay.
in that case. But no, that should make sense to you. I hope it does. Similarly, and I'm not even going to go through as much explanation with this one, but if f2 were going like this, and this is angle theta, and we'll call this theta question, okay? Then the reason why I'm calling it theta question mark instead of theta 2 is because that's what I'm looking for. I don't know what it is. This is f2 sine theta question mark, and this is f2 cosine theta question mark. We cool with that?
Oh yeah.
Okay. So I'm going to redraw. I'm going to redraw this free body diagram to look something like this. I know it goes down with W. Over here, I'm going to make it F1 sine theta 1. I'm going to make it go up with F1 cosine theta 1. All I did was I replaced this F1 with its x and y components. Does that make sense? Because that's what the lab on Wednesday was all about. You can take a vector that is being pulled off with an angle and replace it with x and y forces. Are we cool? All right. You weren't at the lab. I should do the lab with you, though. It's fun. All right. Now, I'm going to replace this F2 with F2 sine theta and F2 cosine theta. Should put a little question mark at the bottom of those thetas. Are we cool? Now, I want to know what force I need to pull, or I need to know what angle I need to pull in order to make this thing not accelerate in the x direction. Right? Is that what they asked? What did they ask exactly?
What to find like Jack's angle
So that it accelerates.
in a vertical.
Okay.
So
it only accelerates vertically. Is that what it's saying?
yeah.
So it only accelerates vertically means it doesn't accelerate horizontally. Right?
Yeah.
All right. If it doesn't accelerate horizontally, what we're going to want to do is we're going to want to look at the x direction. Right? So let's add up the forces in the x direction is equal to mass times acceleration in the x direction. And in this particular case, is m equal to 0?
No.
No, m is 1.3. Is a equal to 0?
No.
It is.
Oh.
Or at least I should say ax. Is ax equal to 0?
Yes.
Yes, because we don't want it to accelerate in the x direction.
Oh.
So the right-hand side of this equation is equal to 0. We're going to add up all the forces in the x direction and have it equal to 0. Does that make sense to you? Now, which forces do you see acting in the x direction?
F2 sine theta.
F2 sine theta. All right. F2 sine theta.
F1 sine.
Wait.
Okay.
Is F2 sine theta positive or negative?
Negative.
It's negative. Why is it negative?
Because it's on the left.
Because it's pulling that way. And if it's pulling that way, and we decided that everything going that way is positive, then it's a negative, right? All right, and then what else do you see? I'm sorry. Look over here.
F1.
F1 sine theta. We cool? So negative F2 sine theta plus positive F1 sine theta equals 0. Can I solve for theta? Sure. F1 sine theta is equal to F2 sine theta with a question mark. All I did was I added F2 sine theta to both sides. Confused? No? Yes? Good?
I'm good.
F1 sine theta divided by F2 is equal to sine theta question mark. So theta question mark is equal to the sine inverse of F1 over F2 sine of theta 1. Plugging that into our calculator, theta question mark is equal to the sine inverse of 11 divided by 7 times the sine of 28. All right, so 11 divided by 7 times the sine of 28, and the sine inverse of that number, is 47.6, or 47.53. 47.54 degrees. What did they say the answer was?
I don't know. I don't know what the answer is.
48.
Okay, that's
They said 48 degrees. I said 47.54. It's the same thing. We cool? All right, now, the second part of the question they ask is, what is that acceleration?
Oh wait, but it says given the weight and has a magnitude of 12.8 newtons.
What is it?
12.8 newtons. Like, there's another number part of it.
Oh, given that its weight is... Oh, yeah. But I didn't need that in this case.
Oh, okay.
What Alice is saying is W is equal to 12.8 newtons? Is that what you said?
Given that its weight has a magnitude of 12.8, yeah.
And I think that comes from 1.3 times 9.81.
Oh, never mind.
1.3 times 9.81 is 12.8.
Oh, never mind. Oh,
So we didn't even need for them to tell us
okay.
the weight. We could have calculated it out ourselves.
I just thought it was important. Just
No. And it is important. It is important. It's important in this part right here. So we figured out the angle that he's pulling at. 47 degrees, 48 degrees. Cool? The reason why we didn't need that number for W is because we're only looking in the X direction. And W is only going in the Y direction. See? It's only pulling down, W. So that's why we haven't dealt with it yet. But we will, right now. Now what we want to do is once we know the angle, we can now figure out the acceleration that this thing undergoes. So, if I look at the adding up the forces in the y direction is equal to mass times acceleration in the y direction, Is the acceleration equal to 0? In this case, it was equal to 0. Is the acceleration equal to 0?
No.
No, it's not equal to 0. In fact, we're trying to calculate it. That's how not equal to 0 it is. If it were equal to 0, why would we even try to be looking for it? You get it? So let's figure out what it is. So I'm going to have all of my forces that I add up is going to be equal to mass times acceleration in the y direction. Are we cool? Can you see that, Kaylin? All right. So I have to add up all the forces on this graph that you see acting in the y direction. Name them for me. What forces do you see going in the y direction? What arrows do you see in this picture that is going up and down? That's my question.
F2.
Okay, so I've got F2 cosine of theta.
F1.
Wait.
Oh, okay.
Positive or negative?
Positive.
Positive, good, okay. I have an F1 cosine of theta. Positive or negative?
Positive.
Positive, good. I have a, what else?
Weight.
I have a W,
Minus.
a negative W. And that's equal to
MAY.
mass times acceleration in the y direction. We cool? That's not mass times acceleration times the y value, the height or something like that. This is mass times the acceleration attributed to the y direction. Right?
Mm-hmm.
Okay. Do we know F2? F2 was 7.
So, oh,
Do we know
that's the
theta?
reason. Yes.
That was 48.
47. 48.
Do we know F1?
11.
Do we know theta?
Yes.
Well, I'm sorry, this is theta 1 and this is theta 2. Do we know theta 1?
Yes.
What was it?
Is it all?
That was 28. Do we know W?
12.8.
12.8, which is actually mass times gravity, right? So that's just W. Do we know mass?
Yes.
Can we figure out what AY is? If we know everything else.
Yes.
Yeah, you just divide both sides by half. So you use your handy dandy calculator to plug in 7 times the cosine of 48 plus 11 times the cosine of 28 minus 12.8. Divide that by 1.3. Seven times the cosine of 48 plus 11 times the cosine of 28 minus 12.8. All right, so this is 1.59633 divided by 1.3 is equal to my acceleration in the y direction. Divide that by 1.3. I end up getting acceleration in the y direction is equal to 1.23 meters per second squared. Is that the right answer?
Yeah, I mean it's like really close.
What did they get?
It's 1.2, but
Oh, they just rounded it off.
they rounded it off.
You get it?
Uh-huh.
Does it make sense?
Yeah.
So how would you use something crazy like this? Which, this is a lot of steps, and it looks crazy. It's not as bad as it looks. I guess the reason why it looks so crazy is because
There's a lot of writing.
yeah, and I'm doing a lot of the steps. I'm like breaking it down very slowly.
Mm-hmm.
At this point, you folks should be good enough to just write down f1x equals f1 sine theta. But I take the time to explain, like literally we only got through 2 example problems today.
Yeah.
But I take the time to explain each piece and where do they come from and all that kind of stuff. Because I mean, that's what I'm supposed to do, right? That's my job. But these problems aren't really as bad. I mean, okay, here, let me give you remember how I told you, here's the surefire way to figure out exactly which equation to use, right?
Mhm.
For the four kinematics equations?
Yeah.
All right, here's the surefire way. Is there a dog? Oh, is it right outside?
It's like outside.
Oh, interesting. Here's the surefire. I feel like Doug from the movie Up. Just like, here's the surefire squirrel. Anyway, here's the surefire way to figure out the answer to this. This is the steps you always take. Okay? Step 1, draw the problem. That's what we did.
Mhm.
Step 2, draw a free body diagram. That's basically just draw the same problem, just make it a little bit more clearer. I wouldn't even use numbers there just because it adds to the chaos. Cool?
Mhm.
Oh, I forgot. Step 0, make a coordinate system. Decide on how you want to call your coordinate system. For these ones, standard always works fine. So just stick with that. Step 3, and this also should be kind of step 0 really, is for all the vectors that you see that are going at an angle, break them up into their x and y components. That's all of this mess over here. Cool? This doesn't really take any brain cells, it just takes pencil power. Step 4. I like to redraw my free body diagram to reflect the things I calculated here. Cool? Because the reason why I do that is this picture is just as good as this picture. It's just the thing is when I add up all of my forces in the x direction, it's easier to look at this picture than it is this picture. Does that make sense? All right. Step 5. You're going to add up all the forces in the x direction, and then step 6 is add up all the forces in the y direction. You can interchange those two. You can do the y direction first or the x direction. It doesn't really, well, I can't say it doesn't matter. It depends on what you're trying to solve. In this case, the first question they asked us was, what is the angle such that the force would only be going in the x, or only be going in the y direction, and no force would be going to the x direction. In that regard, this is you need to do the sum of the forces in the x direction. Does that make sense?
Mhm.
And then the reason why I say you should have done that one first and do this one second is because our answer here depended on what we got for our answer there, for the second part. So you're just adding up the forces in the x direction and then adding up the forces in the y direction. I can't really, the only more complicated thing I can do to this is add more forces. Just go add force 3 and force 4 and force 5 and all that kind of stuff. It doesn't really make, all that means is it just makes this step even longer and a little bit more writing, but it doesn't really make things harder. It just makes more work for you. You get it?
Yeah.
There's an entire field of engineering called statics, and it basically means they just say A is equal to 0, and this A is going to be equal to 0. And here, look. When I was teaching at Leeward Community College, I was teaching statics and dynamics. This is an entire semester of engineering. And this is a really hard class. And this is an entire semester of engineering. So this is a full year of engineering. The hardest you can go at community college. So it's like 230 or something like that. That's the highest they go at the community college level. And all statics is is sum of the forces is equal to 0. And then they get deep into it. It's hairy, and we're talking about like crazy stuff. And it's really that's all of this is. It really is just this equation repeated over and over your entire year. You do that, or entire semester. And then all dynamics is this is not equal to 0. Because dynamics is moving, right? Something that's dynamic is moving. So your acceleration is not 0. Something that's static is still. So your acceleration is equal to 0. So there we go. Engineering, check. Yes, it does get much more complicated. Engineers tend to make this thing much more complicated. That's fine too. I have the utmost respect for them. But, all right. Anyway, I hope that makes sense and helps and all of that kind of stuff.